Hello ib3 students. Our next video lesson about moment of inertia. Today will be a little bit more mathematics. Moment of inertia. Okay, so I hope that you try to derive formula for moment of inertia of typical cylinder. Typical cylinder means uniform cylinder, okay? And axis which travels through the center of mass of the cylinder and through the center of cylinder. Let me draw. Okay, so let's imagine that you have a cylinder of radius capital R. Okay, let me copy this, it will be useful. And height of L. So this is our cylinder. Okay, so in general, radius of the cylinder is R and height of the cylinder is L. Let me draw it. So this is L. Okay, and this is R. And we want to find the moment of inertia of this cylinder around this axis. Let me draw it. Axis which travels through the center of the cylinder, like this. Okay, I hope it's visible. So this axis is here inside the cylinder. Okay, so we know that for point mass, moment of inertia is given by formula I is equal m times r squared, where m is mass of this point and r is a distance from the point to the axis, okay, to the rotational axis. So let's identify in this cylinder, let's identify something like a small cylinder of radius small r, but let me draw. Okay, so let's imagine that here we have a cylinder, okay, which is inside this huge cylinder, and one more, because finally I want to operate on this ring. I hope it's visible that here we have something like a ring, okay, which is a part of this huge cylinder. Maybe it is good to copy this here. I hope the size will be the same or similar. And the second one. Okay, like this. So inside we have something like a pipe. Oh, it should be straight line, like here. Okay, inside we have something like a pipe, which is infinitely thin. So this radius I'm going to describe by small letter r, and thickness of this pipe, so this I'm going to use dr, d like difference or infinitely small. Is it clear? So what did I do? I've divided this huge cylinder into a infinite number of small cylinders, each of thickness of small, not cylinders, but something like rings of height of L, each of thickness of dr, and each next is at the distance from the axis of rotation of r plus dr. Oof. So let's look. The idea is to find something like the infinitely small moment of inertia by using infinitely small mass, or other words, I've divided this into something which looks like a set of points. Okay, so this is general formula for moment of inertia, and in my situation, we can identify something like d of moment of inertia, like derivative, as a mass times r squared, where r is distance of this infinitely small mass from the rotation axis. Okay? So this is our base. Okay, so what is m? In general, mass is volume times density. So dm will be d volume times density. Our cylinder is uniform, so density of each part will be the same. But what is dv? V, volume, is volume of this pipe. So this is surface area times height. Okay, but this surface area, so this dA, is the area of this flat ring, this ring. Oh, this one. So what is it? This is area of this huge circle, so pi r squared, but r of this huge is r plus dr. You see, r is to this point and dr is the thickness, minus of the inner one, which is pi r squared. Okay? I can write this in pi r squared plus 2r dr plus dr squared minus pi r squared. But what is this dr squared? If dr is infinitely small, then dr squared will be close to 0. So I can assume that this is 0, obtaining pi r squared plus pi 2r dr minus pi r squared here, and pi r squared minus pi r squared is cancelled, so I have 2 pi r dr. Oof! Okay, so now combining all together. dv is dA times L, so it can be written as 2 pi RL dr. I've replaced dA by this 2 pi r dr. dm here is dV times rho, which is 2 pi RL rho dr. But what is rho? Rho is density, so this is total mass over total volume. Mass of this huge cylinder is m, but what is the volume? Volume of this huge cylinder is pi radius of the cylinder squared times L. Okay, so finally equation for dm looks like 2 pi small r L rho times sorry, not rho, except rho I have mass over pi capital R squared L dr, which is pi can be crossed, L can be crossed. Finally, I've obtained 2m in numerator over r squared in denominator times r, this r, times dr. And finally this di is dm times r squared, so it can be written as 2m over r squared times radius to the power of 3, because r2 and this r, dr. Oof, we are very close to the end. Okay, how to find I if di is given? Of course, by integral. Okay, typical integral of di results in I, and integral of right side we have 2m over r squared, r to the power of 3 dr. And what is we have to take integral from the very small, so from 0 to the edge, so to r. Okay, but what is constant here? Constant is mass and radius. So finally we have something like this. Okay, it's easy because 2m over r squared is 2m over r squared, and integral of r to the power of 3 from 0 to r is 1 over 4 r to the power of 4. So finally this 2 is crossed with this 4 and we have half. M is M and R2 with R4 gives R squared. So finally for the cylinder, moment of inertia of the cylinder is equal half of its mass and squared radius. Oof, a lot of mathematics today. Okay, I'm happy that we did this. I hope that you tried to do this. It's difficult or easy. In my opinion, it's not too difficult. There are 2 steps you must pay attention. First step is here, yes, assumption that dr squared is equal to 0. And second step here, you must replace density by mass over volume or by mass over pi r squared times L. What is important here? Moment of inertia of cylinder is not doesn't depend on its height. We have no L in this. It's only about distribution of mass. Is it clear? So it doesn't depend on the height of the cylinder. Okay, please copy this, check it again. I'll write as heading of this movie that you have to try to do this working alone at the very beginning, so you can turn the movie on after you will try to do this. And your next activity is by using similar way, try to find, I'm changing slide, try to find a moment of inertia of typical uniform rod. So let's imagine that you have rod. Okay, and my rod has a thickness, but of course the assumption is that this is infinitely thin. And you have axis which passes through the center of mass of this rod. Okay, so I can assume that this rod is rotating along this axis. Yes, and you can use the same. You can use the moment of inertia of a point. Okay, well, you can start with this. Practically, in each shape, you can start with this equation. And in this case, you have to divide this rod into sections. Yes, each section at the distance of, let's say, small r, and of thickness of dr in similar way as we did in the previous slide, as we did with the cylinder. Remember, when axis passes through the center of mass, in the other side you have exactly the same section, like a brother or sister, okay, which is at the same distance and has the same thickness. And integration should be done along this. Okay, remember that this the length of this arrow is half of the length of the rod. Is it clear? So you have to start with the center, and this part has a length of half of L. And the rest is very similar. So this is activity for now. Please do this. Use only my movie. Don't try to find a final solution. Let's check. Let's try to do this. Okay. If you have any comments, suggestions, please write a post below this movie on Google Classroom. And if you feel good in physics and in mathematics, you can try also to derive moment of inertia of, let's say, a plate. Okay, so this is activity number 1. Activity number 2 of a plate. Let's imagine that you have a plate of side of A and side of B, which are given, and you have axis which passes through the center of mass of the plate. Plate is of course uniform, and mass passes through the center of mass, so plate is rotating along this. Okay, If you don't want to do with the plate, you can use a cuboid. Okay, but this is more advanced than the plate. So when you will finish rod, please do with the plate. Use my movie and my method, which was presented in the case of cylinder. So let's say that activity number 1 is obligatory. You have to know how to do this in the case of rod, and activity number 2 is not obligatory. If you want to try, let's try. If not, then not. And I think that it was the last lesson about the moment of inertia. Next meeting I'm going to focus on the dynamics of fluid, Bernoulli law, and something different part of physics. Okay, so thank you for watching. Good luck, stay at home, and bye.